All right, let's welcome our next speaker, Vinayak Mehta. Vinayak is a software engineer and an active open source contributor. Hi, Vinayak.
Hi, can you hear me?
Yeah, I can hear you. I still remember your talk from the last year about command line applications and interfaces was a really good one.
Thanks.
Yeah. So today, Vinayak is going to talk about writing Python C extensions and cross-platform wheels. Very nice. So over to you, Vinayak. Good luck.
Thanks. So, hey everyone, I'm Vinayak, and today we'll talk about how we can write Python C extensions and package them into wheels so that they're installable by users on any major operating system straight from PyPI. This is the basic outline of the talk. We'll write a basic extension module using the Python C API, then see how we can do that using PyPI 11, which is a package that offers seamless operability between C++ and Python. After that, we'll briefly look into shared libraries and dynamic linking and see how we can build wheels for our extension module and finally automate wheel building using CI build wheel. The goal of this talk is to give you a good starting point for how you can go about building wheels for your extension modules. The tale begins at the Recur Center, which is a self-directed educational retreat for programmers in New York City. Last year in August, I started my RC batch with the goal of removing a platform-specific dependency from Camelot, which is a Python library that can help you extract tables from PDFs. The dependency is used to convert a PDF to a PNG so that Camelot can do line recognition and identify tables on a PDF page. The problem with this dependency, GoScript, which is a large PDF interpreter written in C, is that it isn't available to install from PyPI. Users need to install it using the system package managers like apt, pacman, or brew, etc. And on Windows, they need to go to the downloads page to get the exe installer, and then hope that Camelot, which is installed from PyPI, works seamlessly with GoScript. In the past, there have been instances where users would install the incorrect GoScript version for their system architecture, leading to seg faults, or Camelot would not be able to find the GoScript executable on the path, leading to an import error. This led me to search for a pure Python PDF to PNG converter, which could be installed directly from PyPI. I wasn't able to find one in pure Python, but I found a C++ library called Poplar that has a CLI utility called PDF to PPM, which could let me do this. I was able to write a wrapper on Poplar called PDF to PNG, which takes in the path to a single page PDF, converts it to a PNG, and then writes it to the given output path. I was also able to build wheels for every major operating system and then include PDF to PNG as a requirement for Camelot so that it can be installed directly from PyPI. In this talk, I'll describe all the steps I follow to package the PDF to PNG C extension module, which depends on the Poplar shared library. On a side note, if you're interested in other things I've worked on during my RC batch or what it feels like to do RC virtually from another time zone, you can check out my blog where I wrote a blog post for every day of my batch. So CPython, the reference implementation of Python, as the name suggests, is written in C. It exposes a rich API using which we can extend Python's functionality. The main use cases are writing extension modules so that we can use C or C++ modules in the Python interpreter and embedding Python as a component in a larger C or C++ application. We're going to look at the first use case in this talk. We're going to look at how we can write an example module which just lets us add two numbers. So we start by creating an example.c and including the python.h header file, which should give us all the functions and macro definitions needed to use a Python C API. Since all Python objects are treated the same way by Python, the programming language, they're also represented by a single C type by CPython, the reference implementation. In CPython, everything is a Py object. This is what a C function to implement a add Python callable looks like. It takes in a pointer to the self Py object and a pointer to the args Py object, which will contain all the arguments that we pass to this function. We then define two long integers a and b, and since we'll get all the args that we pass into this function in the args Py object, we can use a PyArgParse tuple function to parse those parameters into individual variables. You can think of it like scanf from C. Here we are parsing two long integers from args and storing their values in a and b. And L is a format unit for the parameter that we want to parse. And there are two of them, LL, because we are parsing two long integers. The string after the colon after LL is used as the function name in error messages. And L is not able to parse our args and returns false. We need to return null to raise an exception and pass it up the call stack. Then we define two Py objects PA and PB, and then use a PyLong from long function to convert C longs A and B to two long Py objects PA and PB. And finally, create another Pi object called R, which stores the result of the Pi number add function on PA and PB. In the end, we return R, which is the result of the addition. But before we do that, we need to use PyDecref to decrease the reference count for PA and PB, the two Pi objects that we created. This will ensure that PA and PB are deallocated by Python's garbage collector. If you're writing an extension module using the Python CPython, you need to be aware of Python's reference counting model for memory management so that you do not leak memory. You can check out the resources in the last slide to learn more. After creating our add function, we need to create an array of PyMethod-def structures, which will define the list of functions that our module exports. In that list, we specify the name of our the callable that should be available in Python, the C function, a flag that says our C function should be called with self and args, and finally a function docstring. And after that, we need to create a module definition struct, which holds all information to create a module object. Here we can add the module name, its docstring, and the list of functions exported by the module. Finally, we need to create a module init function called PyInit example, which needs to follow the convention PyInit underscore module name, and call the PyModule create function inside it with a reference to our module definition struct. And that's most of our C extension code. To package our extension, we'll use setup tools. We start by importing extension from setup tools, passing the name of our module, the path to our C code, and then call the setup function with this ext modules list. When we install it using pip, pip will pick it up, use setup tools to build the extension, and install it in our side packages. And if we import it in the Python REPL, we can see that pip use setup tools to build a shared library for our module. And voila, we should be able to use the add callable now. We can also store its return value in another Python object, since we return it from the function. Now let's look at how we can create the same extension module using PyBind11. PyBind11 is a lightweight header-only library that exposes C++ types in Python and vice versa. We can use it to easily create extension modules on top of existing C++ code. So this time we create an example.cpp and include the PyBind11 header file instead of the python.h from before. We create an add function, which takes in two long integers a and b and returns the sum, which is also a long integer. And finally, we use the pybind11 underscore module macro to initialize the module. We pass in the module name as the first parameter. And the second parameter, m, defines a pybind11 variable, which we can use as the main interface to bind our C++ functions. We then define the module docstring with m.doc and add all the C++ functions that we want to use as Python callables with m.def. The first argument for m.def should be the name of the Python callable. Second argument should be the reference to our C++ function. Third argument should be the function docstring, and the rest of the argument should be the parameter that the Python function accepts, in this case, a and b. And that's most of our C extension code using pybind11. Now we get to a set.py, where we again create an ext modules list after importing extension from setup tools. We pass in the name of a module, the path to a C++ source file, path to the pybind11 header files using pybind11.getInclude, and specify the language as C++. In the setup.py, again, we call the setup function with the ext modules list. And finally, we need to create a pyproject.toml, where we define all our build requirements so that pip can install and use pybind11 at build time. We also need to set setup tools as a build backend. Finally, when we install our extension module using pip, it'll then use setup tools to build it and install it in our side packages. And if we import it, we can see that it built a shared library out of our extension module and put it in the side packages just like before. And it works like before too. With pybind11, it's easy to write an extension module or wrap an existing C++ library to create a new extension, in terms of not having to change existing function parameters and return types. The API to write an extension is also a bit less verbose compared to playing with Py objects. With the Python C API, we had to first parse incoming parameters, convert them to Py objects, and then finally return one too. We also had to raise appropriate exceptions, but pybind11 can automatically take care of all of that for us. In the case where I wanted to wrap the PDF to PPN popular utility, I could just take its C++ code with its header files identifiers in the main function and turn it into PDF to png.cpp, where I change the name of the main function, passed into parameters, the paths to the single page PDF and an output PNG, and initialize the module with the pybind11 underscore module macro. And after building it for different operating systems, I could access the C++ convert function in my Python code like this. Let's look at how we can build extension modules that depend on shared libraries. But before we do that, let's briefly look into shared libraries and dynamic linking. To understand shared libraries and dynamic linking, we'll go through an example of how a program might run on Linux. Let's say we have a C program which prints a string called hello world. When we compile it with GCC to get an executable and run it, this is what happens. The program sees that it needs the code for printf from the C standard library called libc, and since it does not have it, it asks the dynamic linker LD for the path where libc is stored. The dynamic linker looks for it, finds it in one of the default paths, and gives it to the program, which can then finally finish executing. Here, libc.so is the shared library, and the whole process of finding it is dynamic linking. Shared libraries are loaded into memory the first time a program that requires them is executed, and if during that time another program that requires them starts executing, it can just reuse a copy that was already loaded into memory. On Linux, shared libraries follow the libfoo.so naming convention. For example, libc, libpng, and libpoppler. This is the shared library search order on Linux. LD first looks into one of the default directories, then looks for all the directories listed in its config file, then looks for any paths on the LD library path environment variable, and so on. You can check out the full list on its man page. On Windows, shared libraries are called DLLs, or dynamic link libraries, and have the .dll extension. The Windows dynamic linker works like this. It does not search for a DLL if a DLL with the same name is already loaded into memory, or if the DLL is on a list of known DLLs for the current Windows version. Otherwise, it will search for a DLL in this order. It will look at the directory from which the application was loaded, then the system directory, then the Windows directory, then the current directory, and finally the directory is listed on the path environment variable. Let's write our own simple shared library on Linux. Let's say we have three different files, mod1c, mod2c, and mod3c, which contain three functions that print some strings. We can compile all of them into a shared library called libfunc.so by passing the shared option to GCC. Now let's say we have a program which expects to call these functions one by one at runtime and then print hello world. We can get an executable for it and link it to libfunc.so like this. And when we execute it, we get an error. It says that the dynamic linker can't find any libfunc.so. Yeah, that's because our current directory where libfunc.so is located is not one of the default directories the dynamic linker looks into. We can temporarily fix this by adding the current directory to the LD library path environment variable, like we saw in the Linux search order. And yay, it works. All the strings that we wanted to print have been printed to std out. Now let's see how we can use that information to package our extension with shared library dependencies into wheels. In part one, we'll look at building shared libraries that our extension module depends on. You might not need to build one because most C or C++ shared libraries that you want your extension to link with might be directly installable through a system package manager. But there could be some instances. For example, you might want to wrap a large private C or C++ code base, in which case you might need to build the shared library first. The build instructions could also vary widely for each C or C++ project that you're looking to build. We'll look at the tools we can use to build our shared library on each of these operating systems. We'll go with the examples for building Poppler and linking it with PDF to PNG. Let's start with Linux. Each Linux distro has its own package manager and its own latest version of shared libraries. That's a problem because you can easily get version mismatches when you compile an extension with specific versions of some shared libraries on one Linux distro and then install it on a different Linux distro, which might have different versions of these shared libraries. To solve this problem, the PyPI came up with a subset of shared libraries that are available on all major Linux distros. If you compile and link your extension with a subset, it is guaranteed to work on many Linux distros, thus calling it Many Linux. According to the Many Linux 2014 spec, this is the shared library subset you can link with, and then stop worrying about these libraries not being present on your user's Linux system. PyPI pushes many Linux Docker images for different versions and architectures to quay.io. So you can pull the image for the architecture that you want and run a Docker container where you can play around with building your shared library. In the case of Poppler, we need to install these packages using yum, and then build the libpoppler.so shared library, which is what we need to link with PDF to PNG. We'll put all these steps in a shell script so that we can reuse them later when we are looking at automating wheel builds. For building a shared library on macOS, we either need a Mac computer which runs macOS, or we can use FastMac, which gives us SSH access to a macOS server on GitHub Actions for 6 hours. It is pretty useful for debugging potential build issues. On macOS, we can install packages using brew, and then build a shared library like we did before. And then again, we put all those steps in a shell script, which we'll reuse later. For building a C or C++ project on Windows, we'll need a Windows machine. And we'll also need to install Visual Studio 2019 Community Edition with the Python native development tools. Windows doesn't come with a system package manager. So one option to install the dependencies that we need is VC package, which is a C++ library manager. Here's how we can use VC package to install the shared libraries that we need. And since VC package won't install shared libraries on the default search path where CMake could find them, we need to specify the VC package installation root directly to CMake. VC package is also installed by default on the GitHub Actions Windows runner. And this environment variable is also available there, which will be helpful when we are looking at automating wheel builds. Again, we put all those steps in a batch script for use later. After installing shared libraries or building them on our own like we just did, we need to make sure our extension is linked with them when it's compiled. We can modify our setup.py to do that. If the extension is built on Linux or macOS, we'll create a list of directories to search for Poplar at link time. We'll also need to create a list of library names that we want to link with. In this case, it's Poplar because we want to link with libpoplar.so. If the extension is built on Windows, we'll also need to add the VC package installation root directly to the search paths and create a libraries list with the names of all the libraries that we need to link with. There are a lot more libraries in this list on Windows compared to the last slide because we're using VC package, which doesn't install the dependencies in a standard search path, unlike Linux and macOS, where Yum and Brew handle that. And if your C or C++ project needs some header files, you can create a list of all directories where they might be present. These are all the ones that Poplar needs. And at the end, we also specify the pybind11 header file directory using the pybind11.getInclude function. We can then create a list of ext modules where we pass in the name of our extension module, the path to the C++ source code we want to build, the include directories, the library directories, the libraries themselves, and specify the language as C++. Finally, we call the setup function with that list of modules. And when we install it using pip, we should be able to use the convert function from our extension module in our Python code. We can also create a wheel for our extension module using pip wheel, which should create a wheel in the current working directory. If you look at one of these wheels, you'll see that our extension module has been built and placed into the wheel, but the shared libraries that it depends on aren't there, which means that if we ship it to PyPI, users who install it would also need to install the shared libraries using their system package manager. Which brings us to our next section on how we can bundle shared libraries inside our wheel so that users don't need to install them separately. On Linux, we can use audit wheel, another tool that PyPI has put out. You can check if the many Linux wheels that we built are compliant with the shared library subset that we saw earlier, and also bundle shared libraries which are not in the subset into the many Linux wheel. Here's how we can use it on the wheel we saw earlier. We run audit wheel repair with output directory and the wheel we need to repair as inputs. In our case, we temporarily add the Poplar build directory to LD library path because it's not one of the default directories LD can look into to find libpoplar.so. And if you look at the wheel again, we can see that all the shared libraries that our extension needs are nicely bundled into the wheel. And their names are also mangled with a hash for uniqueness. On macOS, we can use delocate, which works in the same way as audit wheel. We can list all the dependencies for a wheel using delocate list steps, and then run delocate wheel with output directory and the wheel that we need to repair as inputs. Again, we add the Poplar build directory to the DYLD library path, which is the same as LD library path, but for macOS. And again, we can see that all the shared libraries that our extension needs are nicely bundled into the wheel itself. On Windows, because of the DLL search order, we could basically place all our DLLs in the same directory from where our extension loads, which is the first path in that search order, and we should be good to go. Which means that we can copy over all the DLLs from the VC package installation directory and specify the package data keyword argument for the setup tools.setup function. So we make a minor tweak to our setup.py by adding a copy DLLs function, which finds all the DLLs in the VC package installation directory and copies them over to the directory where our built extension will be present. If the platform is Windows, we call the copy DLLs function and add the star DLL pattern to the package data like this, so that DLL files are included in the wheel that we build. And if you look at the wheel, all the DLLs are present there, and our extension should work. In case where your build process puts DLLs into another directory, which is not the same directory as your built extension module, you can use a windll.load library function in your module's init.py to load the DLL before anything else happens. And since Python 3.8, you can also add a DLL directory to the DLL search path using os.addDLL directory. When bundling shared libraries with generic names like we just did, we could run into and contribute to DLL hell. If you remember the Windows DLL search order, the system won't search for a DLL if a DLL with the same name is already loaded into memory. which means it's possible that the DLL versions that we ship with a generic name might not play well with DLL versions that other wheels ship with a generic name, and vice versa. Depending on your particular scenario and needs, you can go the DLL mangling way, where you mangle the names of all the DLLs like audit wheel does, and then update their import tables to reflect the newly mangled names. To do this, you can write a script which unpacks your Windows wheel, recursively looks for DLL dependencies for the extension module in the VC package installation directory, mangles their names using their SHA-256 hash, and copies them into the same directory as your extension module. It should then modify the import tables for your extension module and each DLL using a library called macho mangler. And finally, it should zip everything again into a wheel. This is what the Windows wheel looks like after those steps. You can see that the DLL names are mangled with their SHA-256 hash, and their import tables are also updated with those mangled names. You can also check out del wheel, which works like audit wheel and allocate, but on Windows, and does these DLL mangling steps that I just described. Finally, let's look into how we can automate wheel builds using CI build wheel and GitHub Actions. CI build wheel is a useful tool which can help us build wheels for all platforms with minimal CI configuration. This is how it works. We create a GitHub workflow, which will get run on each push of a tag. In the environment variable section, we specify the CIBW build variable with CP3 ? Which should build wheels for all Python 3 minor versions on Linux, macOS, and Windows, except Python 3.5, which we specified in the CIBW_skip variable. We can specify all the commands that should run before building our wheel on Linux using the CIBW before build Linux variable, where we pass in the shell script that we created earlier. And then we also specify how our many Linux wheels should be repaired with audit wheel using the CIBW repair wheel command Linux variable, which contains the same command that we saw earlier. We can do the same for our macOS build script and specify how we want to use delocate to repair our macOS wheels. And we do the same for our Windows build script, then specify how we want to use del wheel to repair our Windows wheels. We then define a matrix of operating systems we want to build wheels on, check out our GitHub repository, install Python. On Windows, we also need to set up the developer command prompt for MS Visual C++, which we can do with this GitHub action. We then install CI build wheel and run it like this, where we specify wheelhouse as our output directory. We do the same for Linux and macOS like this. And in the final step, we upload the built wheels as a build artifact, which we can then download and manually upload to PyPI. Or just add another job, which can do that for us automatically. The first step would be to download the build artifact from the last build job, and then upload it to PyPI using the PyPI publish GitHub action from PyPI. We just need to configure our PyPI token as a secret, and we should be good to go. And when the build and upload job finishes, we should be able to see our wheels on PyPI. And that's mostly it. When I was playing around with PyPI 11 and that Julia Evans wrote some years ago, I tweaked it a little bit so that it resembles a PyCon Australia mascot Curly Boy and added various types of food emojis that it can eat. And I built wheels for Linux and macOS so that it can be installed just using pip. If you're interested in its source and the build process, you can check it out here. Here's all the code that you need to that you can check out to learn more. And here are some awesome talks you can watch to learn more about Python C extensions and their distribution. Thank you for listening. You can reach out to me on these links.
Thanks a lot, Vinayak. It was really a nice talk. We have two questions. I'll read them out for you. Let me put them on screen as well. So PyBind 11 infers versions 11 of C++. What about the newer versions of C++ like 14 and 17?
I think I didn't show the PyBind 11 build.ext class. That's in one of their examples that they put out in their GitHub organization, which lets you add like other C++ versions too. So like I can post a link in the room later.
Sure, that would be great. Hope that answers the question. The next question is about how to disable shared library DLLSO discovery on Windows Linux.
Oh, I'm not sure about the question. Why do you want to disable their discovery?
Okay, I think this can be taken offline then.
Yep.
Maybe, yeah. So, yeah, that was a really nice one. I see people typing in the Matrix channel. So if you have any more questions, please feel free to reach out to Vinayak on the Breakout Optiver channel, and he would be happy to answer them all. Thanks once again, Vinayak. I really enjoyed it. It was a pleasure listening to you once again this year.
Thank you.
Thanks. Bye.
Bye.